let's get on with it then. We are going to say just a few more things about Euler paths and Euler circuits. Most people seem to do quite well with these on the test. There were a few questions about that. Let me just say, often, I would say usually, no Euler path or circuit exists. I'd say usually just because, remember, what determines if an Euler path or circuit exists is about the odd degree vertices. Look at these suckers coming in late. They missed the big announcement. Odd degree vertices are what Euler circuits and paths are about. Remember the rule is, if you have all evens, there's an Euler circuit. If there's two odds, there's an Euler paths. And if you have any more odds than just two, then there's nothing. No Euler circuit or Euler path. And usually, if you just make up a graph at random, it's probably going to have lots of odds in it, right? There's no good reason that it's always going to have evens. So it is usually the case that there is no Euler path or Euler circuit, right? And in such situations, the best we can do, this is what we're going to talk about today. What can you do if there's no Euler circuit? You still, in many real-world situations, you still want to try to do your best not to repeat any edges. That's what the Euler circuits are all about. What I want to talk about today is sort of how do we try our best. So the best we can do is what's called a minimum duplication circuit. A minimum duplication circuit. So what this means is, I'll just write usually min dup circ means we cover all the edges with as few as possible repetitions. Now, an Euler circuit has no repetitions at all, but usually that's not possible to do. So a minimum duplication circuit means we use every edge, but repeat as few edges as possible. This is called a minimum duplication circuit. So what I want to talk about today is just, if I show you a graph, how can you find a minimum duplication circuit? This is useful when there is no Euler circuit, which is actually very often. If I just show you a random graph, it's probably not going to have an Euler circuit. This is the sort of second best, the best you can do in such a situation is called a minimum duplication circuit. So, how do we find them? That's our main, topic for today. How do we find a minimum duplication circuit? All right. Here's a, typical example. This is my old Mr. Plow example. Let's say Mr. Plow lives down here at the star and wants to drive across every edge once and end up back at home. This is what Mr. Plow likes to do. Wants to cover each edge. Without repeats. But that's actually not possible, right? Because if you look at the degrees on this graph, you will see I got 2's in the corner. That's a 2. That's a 3, a 3, a 3, a 3, and a 4. So Mr. Plow wants to cover each edge without repeats, but that's actually not possible here. So the question is well, then what's the best he can do? Does he have to repeat one edge? Or maybe can he do this? I mean, is it even possible to do it just repeating one edge? Or is it necessary to repeat 2 or 3 or how many? So the question becomes now, what's the best we can do? And this is a more complicated question than just, is there an Euler circuit or not? I mean, if you know the rule, it's very easy to answer. But what's the best we can do here? That's more complicated, right? In particular, I would ask, must we repeat, or I want to say, can we Can we do it only with one repetition, or do we need more than that? That's what I'm trying to say here. Can we do it with only one repeat? Or do we need more than one? Actually, in this example, I mean, it's not immediately obvious, but the answer to that question is no. Actually, in this example, you have to repeat more than one edge, but we're going to talk about how you would actually figure that out. In fact, in this example, I believe you need to repeat 4 different edges, but we're going to talk about how you would look at the graph and actually figure out how many of those edges need to be repeated. All right, I want to come back to that example because this is slightly more complicated. I want to start with some simpler examples first. The basic strategy, though, is called Eulerize the graph by edge doubling. This is the basic strategy. Eulerize the graph by edge doubling. Eulerize means you add extra edges until it has an Euler circuit. That is, you add extra edges until all the degrees become even. And actually, we're not going to add just any edge, but we're going to double the edges. That's what I mean by edge doubling. You look at certain edges on the graph, and you double up some of them to turn all the degrees even. Your goal is to make them all even so that you can find an Euler circuit. So here's a simple example. What about this graph here? All right, this graph. You should look at the degrees, first of all. That's the important thing that you want to focus on. In this case, they are 2, 3, 2, 3, like that. All right, and I'm gonna kind of circle the 3s there because I don't like those 3s. All right, the odd ones are the ones that give you a problem, and your goal is to make all the degrees even. Make all the degrees even by doubling existing edges. And I'll say in a moment why in particular we want to double edges. Actually, you don't want to add new edges that didn't exist before. You want to double up some existing edges. Anybody see an edge here that I could double up which would take care of the odd vertices? I want to make them all evens. Yeah, the one across the middle, right? It is connecting those two 3s. And if I were to double it up by adding, I'll do this in red, like that. Now these 3s turn into 4s, right? And this generally is going to work. If you have odd degree vertices, you want to double one of the edges that hits the odds, because then you'll be increasing the degree by 1 and it'll turn into even, right? So make all of the degrees even by doubling the existing edges. And then what we got now, I'll just redraw the picture here. Now it looks like this, right? And it has 2, 4, 4, 2, all right? This is called the Eulerized graph. Some people say Eulerized. Those people are wrong. It's Eulerized. All right, the Eulerized graph. It's called Eulerized because now that I did that, it now has an Euler circuit. And so I can find an Euler circuit in this graph. So in the Eulerized, we can now find an Euler circuit. This one is fairly easy to just eyeball. If you had a larger graph, you would use Fleury's algorithm. That was the technique we talked about last time about drawing edges but avoid bridges. We can now find an Euler circuit. I'll just draw it one more time here. In the Eulerized graph is like that. And let's just say I'm going to start up top. This one is small enough you can pretty much just sort of make it up as you go and everything will work out great. I'll come back around in the middle here, down there, over there, and back up. Sorry, back up to where we started. All right, there's my Euler circuit on the Eulerized graph. What's the point of all this? Remember, really what we're looking for is a circuit on the original graph. So this is an Euler circuit on the Eulerized graph. On the original graph, this is a circuit with one edge repetition, because we're going across the middle twice there, right? So on the original graph, the OG, if you will, that was the original graph. The Euler circuit that I just drew up there corresponds to a circuit on here which duplicates only one edge. And it looks like, if I'm just drawing the same circuit again, it goes down here, across the middle, back across the middle. That's my edge duplication. And then around the outside. All right? So this is now a minimum duplication circuit. And just so we all know, it's duplicating one edge, the one across the middle. All right? This is why when we Eulerize the graph, you're not allowed to create new edges that didn't exist before. You have to do it by duplicating the existing edges. It's because the whole point of this is to translate this picture back onto the original graph, where you're running over some of the edges more than once. All right? So this is our minimum duplication circuit, and it repeated one of the edges. All right? Any thoughts about this? This is the process for making a minimum duplication circuit. You make the Eulerized graph by doubling some of the original edges. You draw the Euler circuit on that, and then you translate that back into a duplicating circuit on the original graph. All right? I want to try some more examples. If, any thoughts about that one? I got some for you to try also, but I want to look at some more complicated ones. That was a fairly simple one, where in this case we had to only duplicate one of the edges, right? I had two odds, and I just joined them up by an extra edge, which turned them both into evens. What about some kind of larger graph? Here's a bigger sort of rectangular graph here. Let's just Eulerize this one. Eulerize. Remember, that means first I should look and identify where are the odds. Those are the ones which I need to kind of repair by duplicating edges. So here, when I look at the degrees, these are 2's in the corners. 2 here. 3's sort of in the middle on the sides, and 4's on the inside. What interests me are the 3's, right? And you want to duplicate edges here in order to turn all those 3's even. I'm going to circle them just because, like I said, those are the ones that I'm focused on. I want to duplicate edges to turn those 3's even. Really, they're going to turn into 4's because when you duplicate one of their edges, it adds a 1 onto them. Anybody have a strategy here? I mean, obviously, just looking at this, I can say immediately, you're going to have to duplicate more than one edge here, because any one edge you duplicate, at most it can turn 2 of those 3's into 2 4's, but you're going to have to do this several times. And you want to find a decent strategy to do this. Anybody see what's a good choice of the edges I can duplicate? What do you think? Yeah, connect up the 3's. So I'm going to duplicate each of those edges sort of in the middle on the sides. This one, this one, this one, and this one. All right? Now they all turn into 4's. So in this particular graph, you need 4 edge duplications in order to make a circuit. Right? It's because, I mean, there's no way to turn all those 3's even. How about, here's another one. I'm not going to bother finishing. I mean, you could also draw the Euler circuit, but I just want to talk about the Eulerizing process. How about this? Here I have 3, 3, 3, 3, and 4 in the middle. Anyone want to suggest how many edges do I have to duplicate, and which ones should I do? Which ones should I dupe? Yeah. The outsides? You mean like all 4 of the outer edges? I think actually that might be too much. If I do say, this is a good idea because you want to deal with all of those 3's, but actually if I put, say this one now is a 5, if I duplicate all of the outside edges. Anybody have a slight variation on this?
You just do like the top and the bottom.
Yeah, you only want to duplicate sort of 2 and 2. You could do the top and the bottom, or the 2 sides. I'll do the 2 sides. It doesn't matter either way. Right, now those 3's have been turned into 4's. If you also do the top and the bottom, you're going to make them into 5's, which is, you went too far, right? So, yeah, this is the way to Eulerize on this picture. I took the odds. You basically want to pair up the odds, if possible, pair up the odds and connect them by doubling edges, right? This is your best bet. Take them in pairs, and you don't have to add even more edges than that. Pair up the odds and connect them by doubling edges. So I would say that one, or if you prefer that same example, you could do it this way, right? It doesn't matter, but you take those 3's which are in the corners, you take them sort of 2 by 2 and connect them up with edges, and then it becomes Eulerized. All right. Sometimes it's not that easy. Here's a case in which you can't really pair them up, so sometimes they don't pair up. Here's an example of that. How about that? This is like a sumo guy or something. Let's try and do this for this graph. As always, you look at the degrees everywhere. I see 2 odds in this picture, and they are here and here. Those are 3's. Everything else is either a 2 or a 4. These are 4's, right? These are 2's. 2's out here, that's a 4, that's a 4. So what am I going to do in this case? The problem is, I said sometimes they can't pair up. Well, there are 2 of them, so obviously you can consider them as a pair. But this is not allowed. You cannot just add a big edge like that. Because, remember, the whole point of this is doubling the existing edges. It's because we're trying to view this as a circuit on the original graph which repeats some edges. You can't just make up a new edge out of nowhere. So you can't invent a new edge connecting them. What are we supposed to do then? I have to double edges which somehow turn those 3's each, probably into 4's, but we have to make them even. Anybody have an idea? Strategy? Yeah?
If we connect the 3's into the 4's on the side of the head, and then double up the line that connects the 4's.
Yeah, this is a great idea. I think what he's saying is double like this, and then like this, and then like this. All right? That actually will work here. It turns the 3's into 4's. And now it also messes up these 4's, but each of those 4's gets increased by 2 because I added an edge on either side. And so those 4's actually become 6's, and everything's even. All right? So the strategy here, actually, this will work in general. If you can't draw just an edge between the odds, so if we have odds with no edge existing between them, that's the problem. That's what we had in this situation. The 2 3's were like far apart, and there was no single edge connecting the 2 3's. If we have odds with no edge existing connecting them, I'll just say between them. Come on. The strategy is you connect them up on a longer path, right? Between that 3 and the other 3, there was no single edge, but you can still connect them up by doubling all edges along a path. So if we have odds with no edge existing between them, double each edge along a path. That's what I did there. I considered the whole path going from this 3 across to the other one, and then we double up every edge along that path. The result is it turns those 3s into 4s, it turns those 4s into 6s, but everything is going to be even after you do that. All right? And then, as before, you can draw an Euler circuit on this, and it would represent a minimum duplication circuit on the original graph where apparently you're going to have to duplicate 3 edges on this one. All right? Maybe we could just try that. So in this particular example, we get, I'm going to redraw that graph like this, and then like this, and then the head in the middle. And because after I Eulerized, I got extra edges like this. All right? Can we draw an Euler circuit now? I'm going to try. Let's say starting over here, it doesn't matter where you start really. To make an Euler circuit, you can start wherever you like. Maybe I'll go across the outside first. You can basically go wherever you want as long as you don't cover a bridge, right? As long as you don't cross a bridge among the ones which you have not yet used. Maybe I'll continue going around the outside. Now, at this point, I don't want to turn left because then I'm going to get stuck back at the starting point. So I'll go in here, come up this way, back. So there, right here, is one edge repetition that I just did. They look like 2 different edges on this one, but they represent the same edge on the original graph. I'll come down here, maybe. I'll go back and forth here. There's my second edge duplication, and there's my third one. Like that, all right? We have a circuit with 3 edge duplications here. Those are the 3 ones that we duplicated to Eulerize the graph. So in this case, the minimum duplication circuit requires 3 edge duplications. 3 edge dupes. All right? This is how we do it. How about, sometimes you actually need many duplications, even for a small graph. How about, are there any questions about that one? Everybody's feeling good? I hope so. Just as one more fun example. How about this graph here? Little wishbone or something. How many duplications are necessary here? You should look at the degrees. I see 1, 3, 2, 1, 1, 2. Right? Those are the degrees. The odd ones are what you want to focus on. The are 1 is odd, 3 is odd. All right, so I have 4 odd degree vertices. What do I need to connect up? Well, 2 of them can be connected as a pair, like these 2, right? But the other 2, unfortunately, have no edge between them. What can we do to connect them up?
You have to do all of them.
Yeah, I think we just have to duplicate every edge. This is like the worst case scenario, but in this case, I have these 2 ones. The only way to join them up would be to duplicate everything along this path. And we're just going to have to duplicate every single edge in this case. This is the worst possible outcome where, I mean, it can happen though. Sometimes you really have to duplicate every single edge. All right. So here we need, how many is that? 5 dupes. All right. In order to connect up the odds, you require every duplication. That is the worst case scenario. In the worst case, you'll have to duplicate every edge. There's no scenario in which you might have to duplicate some edges more than once. That actually never happens. All right. Any Any last thoughts about that? I got some examples for you to try. Maybe I'll just sort of summarize the process here. So the minimum duplication circuit process. What you want to do, first of all, is Eulerize by edge doubling. And this involves connect up odds by doubling edges, either individual edges or paths, right? If you're lucky, you can just connect two odds by a single edge, by doubling a single edge, but sometimes you'll have to make a longer path from one odd to another. Connect up the odds by doubling edges or paths. And then make an Euler circuit because you've turned all of the degrees even. So after you Eulerize, you make an Euler circuit on the Eulerized. And then this makes, that same circuit makes a minimum duplication circuit on the original graph. Min dup circ on the original graph. All right, this is the process. I got some for you to try. So I'm going to draw a graph. Your job is to figure out how many edges you have to duplicate and which ones, and then draw a minimum duplication circuit for that graph. I have several examples for you to try. How about that? Well, there's one. Trying to draw nice here. That one. And oh. That's the original Mr. Plow one that I wrote at the very beginning. All right, your final answer should look like a circuit drawn on the original graph which duplicates some edges, as few as possible. I'll give you a moment and then I'll come around and see how you're doing. Look at all the degrees first and figure out where the odds are and try to estimate them out. Okay. This is not allowed to make a new edge that doesn't exist. That's okay. Because this path that you drew is not actually the path of the original path.
That's what I thought.
All right. I'll give you a few more minutes, and then we can talk about them. All right, let's talk about these, because I have one more thing I wanted to say before we leave today. So I did the first one over here. I hope that, as I was going around, it looked like people were feeling good about this one. You identify these threes are the problem. You duplicate this edge to turn them into fours each. And then my actual answer is this. This is the original graph with the circuit which duplicates that edge right there. How about this one here? When I look at the degrees here, this one's, I guess, slightly more interesting. I got 3, 3, 3, 3, and 2 here. So you have to join up these threes in pairs. There's a few different ways to do that, and there's sort of actually like a good way and a bad way, or a few different good ways. I would say join them up like this and this. Rather than, you might be tempted to duplicate this edge in the middle, although if you duplicate that edge in the middle, then you're going to have a hard time connecting up the other two. So sometimes you want to look at what, I see all 4 of these 3s. I want to group them into 2 pairs in a nice way. If you decided to group the 2 middle ones together, then there's no good way to connect up the other 2. I mean, it's possible, but you have to make more duplications. I can do it in 2. If you duplicated 3 edges, it would still work, although that's more than are necessary. Anyway, I'm going to be duplicating those 2 edges. So to write my final answer would be this circuit here. Well, this graph here, right? I'm drawing the original graph again, and I'm going to draw a circuit which duplicates those 2 edges from my original picture. Let's say I'm going to start on top, because it doesn't matter. I'll do this one. I'll do this one in the middle twice. Then come down here, up here. That guy maybe, up top, and then I repeat this one twice, back to the beginning. All right, something like that. Now, if you chose your edges to duplicate slightly differently than me, then you would get a different looking answer. But that's what mine is. Any thoughts about that one? All right, and the last one here. This one, when I look at the degrees, I have 4 odds, but unfortunately they do not pair up in any nice way. You may be tempted in the dark of night to do like that, but this is not allowed. Remember, the whole point of this is drawing circuits which duplicate some of the original edges. You cannot just invent new edges that didn't exist before. What you do has to be duplications of existing edges. There are 2 strategies you could have done on this one. You have to connect up like these 3s, right? And as I was going around, I saw two different strategies. One is like this, double those 2 edges and also these 2 edges. That turns those 2s in the corners into 4s, and the 3s also into 4s. Or you could do it like this, doubling through the middle. Double those 4 edges, and this will also turn them all even. All right. Either way requires 4 edge duplications. And then let's draw the circuit. I'll use this picture on the left. So I'm going to try to draw a circuit here which duplicates those edges here and here and here and here. So I'll start in the corner here maybe. I'm trying to do this sort of in one step, although it may be better to try to draw it on the original graph, or on you may find it easier to draw it on this picture first and then copy it into the original picture. But just because I got a few more things to say, try and do it all at once here. I'm duplicating these 2 edges and back to where I started. All right, something like that. There are many different ways you could do this, of course, but that's how I did it. All right, this requires 4 duplications. I think that's what I said at the beginning of class about the Mr. Plow thing. You need to duplicate 4 edges in that case. Any questions about that one? A little tricky. I don't know. I mean, it's certainly more tricky than just finding an Euler circuit. Is a lot simpler. Minimum duplication circuit. All right. In our remaining 9 minutes, can we talk about a minimum duplication path? This is one which uses every edge with as few duplications as possible, but it's not a circuit. It starts one place and ends in another place. All right. So this is just like the circuits, but this one, I'll just say this covers all edges with as few repeats as possible. But is not a circuit, so it finishes. It starts and finishes at two different points. Starts and ends at different points. All right, this is called a minimum duplication path. And if you remember about the difference between Euler circuit and Euler path, this is the same idea. We are going to do the same procedure, only when you Eulerize, in order to get a path, you need to leave two odds and make the rest even. All right? Otherwise, it's completely the same. So, can I just say, same process, but when Eulerizing, when you do those edge duplications, you leave two odds, make the rest even. All right, and that's sort of all there is to it. You leave two odd vertices and you make the rest even. So, for example, if I was doing this Mr. Plow thing, and I wanted to find a minimum duplication path this time, not a circuit. Again, we look at the odds. I see there are 3, 3, 3, and 3. And we have to somehow join these up. But since I'm looking for a path rather than a circuit, I can leave two of them like they are and join up the other two. So maybe I'll leave the two on the bottom left like they are, and I will add edges to sort of repair these. These are now 4s, all right? And the other 2s are 3s. The other 2s are 3s. I know that's not clear. All right, I'm leaving two of them odd. That's because what I'm looking for is an Euler path, which has two odds and the rest even. So this time, now, our path, remember, has to starts and ends at the odds, right? And it's going to duplicate those two red edges. So in this case, it would look like, maybe I start at this one, and I'll go around here. I'll just duplicate those two edges right away, and then hopefully the rest of it will work out. And I end up right here, surprising nobody, right? If you start at one of those odds, you must end at the other odd. So that is where you should have predicted that I would end up, all right? This is a minimum duplication path. Not really much more to say about that as opposed to the circuits. It's the same procedure, only you leave two odds. All right? Let's just try it. I want to do one more big example here. I'm going to go all the way to the next page. That's how big it is. This is like a big city block. This minimum duplication path is sometimes called the optimal parade route. This is like how the parade goes. You don't want the parade to go down the same street twice, right? That'd be crazy. But they got to cover every street for the kids. Oops. Let's say there's some diagonal streets here. All right. So this is a big graph. I'm not actually going to try to draw the answer, but sometimes, you know, on our test, I suppose our final exam, you might see a question like this. How many edge duplications would be required for a minimum duplication path? All right. This one, it's a real pain to actually draw it because it's such a big graph, but it's not so hard to answer how many duplications would we need to use. So you got to look at all the degrees with an eye specifically for where are the odds. This is a 2, a 4, that's a 3, so that one's important. A 2, this is a 3, that's a 4, 4, 4, 3 here, 4, this is 5. That one is important. That's a 3. That's a 3. That's a 5. That's a 5. A 3. 3. So there are many odds in this one. That's a 2. All right. These are all the odds. it's up to you to decide how to pair them up in the best way so that you are going to have to duplicate as few as possible, and you get to leave 2 of them as odd. All right? Now, when I look at this picture, first I'm going to decide which ones to leave as odd. Anybody have an idea of, do you see one of these that you feel like, maybe I'll leave that one as an odd? Actually, I do see some that I would like to leave the way they are. I did? Yeah.
I would say the topmost 3
This one here? Yeah, why is that?
is isolated.
Yeah, this one doesn't have an edge connecting to any of the other ones. So if I am going to connect this up, it'll actually require me to duplicate 2 edges. So if I'm going to be able to leave any of them like they are, maybe I'll leave this one like it is. That's the only one that really stands out to me as being one that I would like to leave unrepaired, right? So I'm going to leave that 3 like it is. The other ones, hopefully I'll just be able to connect them up in pairs. I'll pair up those 2, those 2. I'm just going to try and sort of do what works. Those 2, and those 2. And I left this other one like it was, all by itself. All right. There's many ways you can do this, of course, but that's one way to pair them up, leaving 2 unpaired. All right. So what's the answer here? How many edge duplications are required? The answer is, show me the fingers. You have that many? 5, right? There are 5 edges. 1, 2, 3, 4, 5. So we need 5 edge duplications. All right. I think that'll do it. So I will see you all 1 week from today. Don't miss me too much.